Hey everyone, and welcome to the Explainer. I am so glad you're here today. If you're a grade 7 learner, or honestly, just someone who loves figuring out how the universe actually works, you are in exactly the right place. We're diving straight into Unit 03 of Physical Science today for a really crucial assessment rehearsal. We're going to explore the hidden world of chemical reactions, look at how matter changes right down at the microscopic level, and clear up some major misconceptions along the way. So get comfortable, and let's decode the secrets of the materials around us.
So here's the essential mystery we're going to be investigating as detectives today. How can invisible particles explain the visible changes in matter? Just think about it for a second. You watch a piece of wood turn to ash in a campfire, or you see a bicycle completely rust out in the rain. You are witnessing massive, visible changes. But the true explanation for what's happening? It's on a scale completely invisible to the naked eye. To solve this mystery, we've got to understand the tiny building blocks of the universe and how they interact with each other. Okay, let's dive into this. Here is our roadmap for today. 1. The visible world. 2. The invisible particle model. 3. Spotting chemical reactions. 4. The law of conservation. And 5. Energy and engineered solutions.
Section 1. The visible world. What we can observe.
Before we can talk about invisible particles, we really have to establish what we can actually observe about matter in everyday life. A huge misconception, especially on assessments, is mixing up physical and chemical changes. Take an ice cube melting on a hot day. That is just a physical change. The state changes from solid to liquid, and the particle motion increases as it warms up. But here's the key. It's still fundamentally water. This substance hasn't changed its identity. A chemical change is entirely different. That's where the magic happens, and atoms actively regroup to form entirely new substances with totally different properties from what we started with.
Section 2. The invisible particle model. Zooming into atoms.
To really grasp how that regrouping happens, we've got to zoom way past the macroscopic world we can see and feel, straight down to the invisible particle model. Down at this microscopic scale, atoms form simple molecules. You can think of these as small, discrete little clusters of atoms bonded together. Some great examples are things like ammonia or methanol. They're just a few atoms linked up, moving around as a single unit, whether they're vibrating in a solid, flowing in a liquid, or bouncing off each other in a gas.
But atoms don't always stop at just a few partners. Solids can also be formed from extended structures. Instead of small, independent clusters, these are large, repeating grids of atomic subunits. Think of sodium chloride, everyday table salt, or even diamonds. A diamond is literally just carbon atoms, but they're locked into this massive, repeating, incredibly strong structure. It's the exact same fundamental building blocks as other carbon materials, just arranged in a vastly more complex way.
Section 3. Spotting chemical reactions. The detective's checklist.
So, if atoms are constantly grouping into molecules or locking into extended structures, how do we actually know when they break apart and rearrange into something completely new? Well, it's time to put on your detective hats. For your assessment, you absolutely need to know this vital checklist. Every pure substance has characteristic physical and chemical properties we use to identify it. To figure out if a chemical reaction happened, you just check these properties before and after the interaction. We're looking at density, melting point, boiling point, solubility, flammability, and odor. If you mix two things together and these properties stay exactly the same, you probably just have a mixture, no chemical reaction. But if those properties change, you've caught a reaction red-handed. Let's apply that checklist in the real world to prove a reaction happened. Think about burning sugar to make caramel, or even burning steel wool, or imagine mixing zinc with hydrogen chloride. If you measure things like the density or the flammability before these interactions and then measure them again after, the data will be totally different. The new substances have different properties from the original reactants, and that data is our absolute proof that a chemical change took place.
Section 4. The law of conservation. The golden rule of matter.
Now that we know how to spot a chemical reaction, we need to know the rules of the game. And there is one fundamental rule that governs every single chemical process in the universe. In a chemical process, we start with step 1, our original substances, which we call reactants. Then comes step 2, the actual chemical reaction, which is really just the atoms from those reactants regrouping. They break their old bonds and shuffle around. Finally, we get step 3, the new substances formed, known as products. Notice what's missing from this sequence. At no point do we say atoms magically appeared out of thin air, and we definitely didn't say any were destroyed. They only rearranged their partners. And here's a crucial point for your assessment rehearsal. The total number of each type of atom does not change. Period.
If you start with 10 carbon atoms in your reactants, you're going to end up with exactly 10 carbon atoms in your products, just arranged differently. Because matter is conserved and atoms are conserved, the mass does not change. The total mass before the reaction is always completely identical to the total mass after the reaction. That, my friends, is the law of conservation of matter.
Section 5. Energy and Engineered Solutions. Making chemistry work for us.
You know, understanding these rules isn't just about passing a science test. It's about shaping the world. When atoms regroup in a chemical reaction, it's not just the properties of the matter that change. Energy is heavily involved too. Some chemical reactions release energy, causing the system to heat up. Others actually absorb energy from their environment, causing the system to cool down, like when you dissolve calcium chloride. Engineers use this all the time. They design and modify devices that intentionally release or absorb thermal energy through these chemical processes. They can precisely control temperature just by changing the type and concentration of a substance.
Which leads us to a pretty profound realization, summarized perfectly by this quote from the science standards. Synthetic materials come from natural resources and impact society. By understanding chemical properties and reactions, engineers can take natural resources and put them through chemical processes to form incredible synthetic materials. We're talking about designing entirely new medicines to keep us healthy, formulating new foods, and engineering alternative fuels to power our cities. Our mastery of the invisible particle directly impacts and improves society.
And that brings us to the end of our explainer. But before we go, I want to leave you with a bit of an engineering challenge. You now know that matter is made of particles, that chemical reactions regroup those particles, that mass is always conserved, and that these reactions can release or absorb energy. So how might you design a device that uses a chemical reaction to solve a problem in your own life? Think about how you could control the transfer of energy to heat something up or cool something down when you need it most. Keep exploring that idea. Good luck on your upcoming assessment, and I'll see you next time on The Explainer.